All right, so thank you again for having me. So my name is Chien-Ming Huang. So today I want to talk to you about robots and in the future of work, care, and learning. My general area is in human-robot interaction, which is really the intersection between HCI and robotics. So I want you to just 10,000 feet of overview of the kind of things that I've been doing the past few years. Happy to chat more if people have questions. But to situate this work a little bit, I want to just talk to you about robots in our current landscape of things, right? So on the one hand, we have robots as a passive tool, right? So an example of this will be surgical robots like Da Vinci, right? So robots in this context, they don't have necessarily quote unquote intelligence. They are essentially tools being teleoperated by human experts, surgeons. On the other extreme of this spectrum is autonomous robot, right? So robot is an autonomous tool. They operate, function autonomously without human intervention pretty much, right? So a good example of this will be warehouse, right? So any big sort of online shopping store, they operate like this way nowadays. Another example of this is manufacturing. Right, so this is car manufacturing. I would say, nowadays the cars are manufacturing pretty much 80 to 90% fully autonomous through the process. And if you look at this, there is no any interaction at all, right? There's only one person that sits outside of the cage, right? There's like that person doesn't do anything, just like monitor, make sure things are going. So this is on the other extreme of robots as autonomous tool. But now we're transitioning to this something in between, where we have human-robot collaborations, where people and robots are working closely as a team, as partners, right? So we're seeing this in manufacturing, and the reason behind this, there are a number of reasons. One of them is people shopping style is different, and they want customized items. We just want to buy things more quickly nowadays. So there are a lot of customization, short product cycle drive a lot of this. And also because of like small and medium-sized manufacturing, they cannot afford fully autonomous floor of robots. And we're seeing this kind of transition not only in manufacturing, but also in a lot of our daily environments, right? In hospital, big supermarkets, they are also piloting robots to do some of the non-human facing kind of work. We're also seeing this in more close to us, like a home environment, learning, hospital, where we see a lot more close interaction between humans and robots. So there are a group of people, myself included, doing a lot of work in this space, trying to facilitate this fluid, effective interaction between humans and robots. And at this itself, I see a lot of opportunities where we can bring this kind of technology to benefit human at large. So today I just want to talk a few projects that highlights our learning in the past few years, right? So I structured this as a way of principles of effective human robot interactions. So we learned a few good principles that all designers and developers pay attention to in the coming years as we continue to develop robotic systems for people. So the first principle I want to talk about is multimodal social behaviors. So I will start with this video, which is about 10 years ago when I started at Georgia Tech. So the interaction here is so this is a video I'm going to play in a minute, but just to give you some context. So the interaction here is very simple, right? The person is going to teach the robot some concepts, right? This is yellow object, this is green object, this is red object. The yellow object is banana, the green object is watermelon, the red object is apple. Right, so by using gestures. So I want you to pay attention to how the person instructs the robot to learn these concepts. Hopefully the audio will go through. Should there be audio? Okay, doesn't sound like we have audio. So let me share again.
Share audio when you shared your screen.
Oops. Well, let's see. I may need to stop sharing. Oh, sure. Does that work?
No, we don't hear anything.
Yellow object.
That was it. At the very end, we had it.
Because can people hear the audio?
Just the very end. Can you hear us?
Let's see people's response.
I don't think you can.
So if you can type in the chat, that would be good. Let me know if you can hear it. Okay. I cannot hear you all actually. All right, so maybe I have a few more. If you cannot hear the others, let me know. But essentially, the interaction here is you see that the interaction is very simple, but it was very awkward in the sense that the robot didn't respond, right? So the person used larger gesture trying to get the robot's attention. So we learned this early on that social responses, behavioral cues are critical in interactions, right? It doesn't matter if it's human or human robot. So here's another example where we flip the role, right? So the robot is the instructor, the person is quote unquote the worker, right? So the robot is going to give instruction to tell the person which object goes to which bin, right? So think about this as a sorting task. So let's take a look. Hopefully the audio will work.
Could you help me put the red object with 4 pegs in a row into the blue box, please?
All right, so let me know if you cannot hear it. Wonderful. So in this case, the robot only used speech as an instruction. And you see that the person was a little bit confused in the beginning, like which object the robot is referring to and which bin the robot is referring to. And if we just add a little bit of behavioral cues to the robot, in this case, it's head orientation, we'll see the interaction is much more fluid. And you'll see the people will pick up the cue very fast and then start to reach out to the object before the robot actually finished the instruction.
Next one. Would you please help me put the tall, blue, square object with 4 pegs into the red box, please?
So even very simple head orientation or gaze cues, if you will, are very effective. People actually pick it up, even if it's very subtle. So the next project I want to talk about is we know that behavioral cues, social cues are important during situated interaction, but there are some people who are not good at this kind of interaction, right? Especially children with autism. Right, so we're thinking maybe we can use social robots as a way to provide or model good, quote unquote, good behavior for these children, right? So there are reasons behind it. These children are more into computers, robots, because they are more predictable, right? So before I talk about this project, let me just play this footage from CNN to motivate this a little bit more.
Children with autism often have a hard time talking with or even looking at human therapists, like this boy. But look at how he lights up with Milo.
We found that.
Yeah, so over the years, we have seen evidence where children with autism, they are more responsive to robots. So we thought there's an opportunity for social robots to be a sort of like a model to provide trainings for these children. So we started to build social behavior into the robot in the idea of doing behavioral intervention, right? So the first core social behavior we built into into the robot is eye contact. Right? So as the person moves around, the robot trying to maintain eye contact with you. So this is a core social skills we want them to pick up. The second core social skills we want to sort of deliver to the children with autism is shared attention, right? So as I look at something, and the robot will look at something with you as if they are sharing attention. So these two are core social skills we want to model through the robot behavior. And on top of that, we build essentially an intervention curriculum that facilitate their interaction, right? So I'm just going to play this demo video to show the interaction between the robot, the child, and caregiver, right?
Yay! Hi, Eliza. It was really hard leaving my family a few days ago when I had to board my spaceship. Goodbyes can be really sad. I held on tight to prepare for landing. Then, I heard my spaceship splash into the water, and I opened my eyes. Looking around, I could see that I was safe and okay. And I could see that I had safely landed on the beautiful planet Earth. Each day I will have some games to play. If we work together and finish all the day's activities, I will earn back a piece of my gear. Thank you so much for helping me fix my space gear. I'm really excited to play. Which game would you like to play first today? Nice choice. Let me get the game ready. Very cool.
So essentially, we build this whole intervention curriculum for the family. And we deploy this system into people's home for 30 days. So the idea is that during the 30 days, each day they will do a 30-minute session with the robot. And through gameplay, the robot will model good, quote unquote, good social behaviors. And we do this fully autonomously. We track where they are looking at. We provide personalize the content that we're presenting to the children. So here's a quick highlight of the results. On the left is the interaction that we want to facilitate is between the child and the caregiver, because ultimately we are not building good human-robot interaction. We want them to pick up good human-human interaction, right? So during the gameplay, the robot will redirect the child's attention to the caregiver if necessary, or redirect their attention to the screen. On the right is sort of a high-level result. So day 0 is the day we go in to deploy the system. Day 30 is the day we go in to take out the system, right? So before day 0, 30 days before day 0, we measure their performance, and after day 30, another 30 days, we measure again, right? So we see their performance throughout these 4 points. One of the things we learned is, the 30-day deployment was effective. Their performance, especially joint attention skills, improved. But then that skill did not sustain, right? So after another 30 days, that their performance dropped a little bit. So this opens up a lot of questions that we are currently exploring right now. Is how long should we actually deploy the system in order to see sustained benefit? But this field project shows you the importance of social behaviors, social cues, and how that we can also use this kind of technology to deliver this kind of social behavioral skills for children with autism. So that's the first principle that we learned in the past few years, is the importance of social skills and behaviors. The next principle that we learn is adaptation. So when we think about human robot working together, they really need to adapt each other, because each person's style is different. So I want to use this project to give you a sense of what I mean by adaptation. So we use this handoff as an example to study this. Right. So if you think about human-human handoff, right? So when the other person is not ready, I'm not going to reach out my hand just to wait for the other person to get ready, right? So I'm see when the person's ready, and I'll reach out. So we, as humans, we actually really good at adapt and coordinate our actions with one another. So how can we build this into robotic systems? So we've essentially got a lot of inspirations and understanding from human-human. So we have people come into the lab to do this kind of handoff. We build a model around it, and test it on the robotic system. So here's some examples of human-human data. So we make it like unloading dishes. So this is very common things people do. They pick up a plate, pass it to another person. The other person places on the cabinet. So this is regular unloading. On the right, we have a secondary task for the receiver. And the goal is to slow down the receiver and see how the giver adapt to the slowdown of the receiver. So pass it to the play. There are some problems on the back of the play, so the person solve the problem and match it to a specific location. And you see the giver sort of change its behavior to adapt to the receiver. So without going into the detail, I'll show you our implementation on robots. Right? So the very first one is what we call proactive robot, where the robot doesn't have any awareness of the person's workload. Right? So it's a very similar task. The robot is a giver, the person is a receiver. So past the play, we give a secondary task for the person to solve the math problem. It's very difficult. You have to solve it on the spot. In this case, the robot did not have any awareness, so it just doesn't care what the person's doing. And you see here, the person was pressured by the robot. So the person was going to put the plate at the corner, which means that I don't know how to solve the problem, I give up. Right? So the person was pressured by the robot and then give up the secondary task. So obviously, this is not ideal, right? So we don't want this kind of human-robot collaboration. So another thing we can do is to make the robot passive, right? So if you're working on the problem, I'll just wait. As you finish up, I will work on my part, right? So this is very much like turn taking. It works very well. The only downside is it's not that efficient, right? So if you think about human-human, if you think about the video I showed you earlier about human-human handoff, people are not doing this kind of waiting. People do a very fluid collaboration. So the last one I want to show you is what we call adaptive, which is the robot's behavior was driven by the human-human data that we collected earlier. So it's the same task, the person working on the math problem, the robot recognized that, slow down its motion. It's still working on the problem, and the robot realized the person still working on the problem and eventually stop. And as the person finished up the task, the robot present the next one. And here, the person was very confident about this handoff. He was not even looking at this handoff at the moment, right? So this is the kind of adaptation, coordination that we would like to have for robots when they come closer in close proximity to do collaborative work with us. We also explore this kind of adaptation in a learning domain. So here, the idea is to have this personalized education set up for children. The setting here is child-robot interaction. The child's learning, doing the math homework. The robot is sitting next to the tablet, which present the math problem. But then the robot keeping track of the performance of child and then provide personalized breaking point. So the idea here is that everyone's sort of attention span is different, right? So instead of having a big block like every 35 minutes take a break, I will sense when you need a break, I'll give you a break. So I'm just going to play this video, and you will see the child was keep getting things wrong, and then get frustrated, and the robot sensed that through the performance that from the tablet, and then provide break for the kid.
How about another problem? The correct answer is 118. Let's try the next problem. The correct answer is 62. Why don't we take a break to refocus? Then we can keep going with the problems. Let's stretch. Follow my lead. First spread your left arm out. Now spread your right arm out. Hold this position for a few seconds. Raise both arms up. Count to 10 with me while we keep our arms up. 1, 2, 3. Great job following along. I hope that was relaxing. Let's get back to our math problems now. Let's do the next question. That is correct.
So we compare this personalized approach to just general traditional approach where they will take a break every fixed amount of time, and then show that there's benefit of personalized strategy for children when they work on the math problem. So the next principle I want to talk about is anticipation, right? So for a fluid human-robot team, it's not just about adaptation, but also anticipate what the other person might do in order to prepare for adaptation. So the way we think about anticipation is to recognize their intent, especially we look at eye gaze. So where people look, especially in situated tasks, tell us a lot about what they might want to do next. So we studied this in, again, it's a mock setting where we simulated sandwich building task. So this is very similar to you go to Subway, you tell your food server, what ingredients you might want for your sandwich, right? So on the table we have different ingredients, and the quote unquote the customer will tell the server which ingredient he or she wants. So look at shop around, look at different ingredients, and we just track where they're looking at as they do the task. So essentially, we have a bunch of data like this. Even a sequence of gaze fixation, can we predict which item, which ingredient the person is going to order? So we essentially translate this into a multi-class classification problem. Here, just want to show you a demo. The person is customer, the robot is the server, right? So on the table, again, it's a simulated setup where we have different ingredients. The person is going to order latest in this case. On the right, we're showing you the likelihood of which item the person is going to order, which in this case is number 8. It's not the best way of presentation, but it's number 8. So let's watch this. So as the person shop around, the robot become very confident about which item the person is going to order. So with this, we did another human-robot interaction study, having people come into the lab to do this. Similar setup, different ingredients in front of them, and the robot is a server, right? So the participants wear gaze tracker, and then based on where they're looking at, we are doing real-time predictions and operation. So you see, I was sitting behind 4 different monitor screens just to get these things working. But it's a fully autonomous system. So let's take a look what it looks like.
Next one.
I would like banana.
You ordered banana?
So here I want to show you before the person actually says something, the robot is already moving toward that direction. Right before banana, it's already moving toward that direction because we have a pretty good sense of what item they might going to order.
Next one.
I would like mango.
Before saying mango, the robot is already moving toward that direction. And this is the kind of anticipation that we would like to explore. Whether or not people like it is a different story. So we compare anticipation versus no, just purely reactive, and show in terms of efficiency, their benefit of this anticipation approach. But participants also comment that it could be creepy because eye gaze is very subtle information. For robots to quote unquote know this kind of information, it's tricky, right? So I think there's interesting discussion here between team efficiency and user experience. So the next principle I want to talk to you about is end user programming. So all the example I've shown you, the autonomous robotic system requires a team of people to do a lot of programming, and not a lot of people can do this. right? And if our vision is to have robots into people's environments to help with daily tasks, at some point we need to let people to customize robotic assistants, right? So how can we bring down the barriers to customize robotic assistant to quote unquote retask the robot without actually coding? So we started to look into this end user programming a bit more when it comes to robotic assistants. And turns out it's actually very difficult to author assistants. Here's one example. The programming style is kinesthetics teaching, right? So instead of sit down to code the robot, coding, the person will drag the robot to provide demonstration of what the robot should do. And turns out it's very difficult. Most people have difficulty doing it just because it's different kinematics, different degrees of freedom, just not very natural programming interface. So we have been exploring different interfaces and systems that can support end user programming. So the first one I want to show you is what we call programming by situated illustration. So instead of sit down to do programming or drag the robots on, I will just illustrate that on an interface. So here we have this projection-based interface that we project on any daily service, right? So this is a regular table. We project interface, and so that any surface can be a programming environment. And to program the robot, you can use very simple touch-based gesture that we all know, right? Swipe, zoom in, zoom out. We provide different tools, right? So we can have a circle saying, here are a group of objects I want you to move. Here is the location that I want you to move to, and then put an arrow in between, right? So the robot will do the pick and place task. So it's through very simple 3 gestures, users can instruct the robot to do pick and play task. We also explore this more in situated setting where instead of doing touch-based, we are doing a situated gesture, right? So I'll just point and then use natural language to tell the robot what objects I'm referring to and where they should go. So here's a demonstration of that.
Move this object over here.
So we have this projection base to provide feedback, but essentially we're sensing where they are pointing. Obviously, we are have a lot of assumptions here that make this very simple in terms of perception, just because we are mainly interested in the interaction elements. So this kind of situated instruction or illustration is much easier for people to do. Here, just we're setting up a different task.
Move the blue objects over here.
So it's a combination of multimodal instruction. We also look at different tools that we can provide to support. As I mentioned earlier, most people, when they provide this kind of demonstration, it's very difficult. And as a result, the demonstrations are not optimal, right? So there are a lot of jerky motions. The path might not be just the shortest path, right? So we essentially implement or develop this demo shop interface to allow people to do post-processing of their demonstration. And the idea is that it's much like a Photoshop, right? You take a photo, but then there might be something not ideal during the photo taking process, but you can do the post-processing later, right? So we have this demo shop that allow people to be able to easily edit their demonstration to cut off those jerky motion element, for example. Here's another approach that we explore to help people provide demonstration. So the idea here, we call it first-person demonstration. Essentially, use their first-person view to capture the most natural way of providing demonstration. Right. So we look at this IKEA's children's chair, which is very simple assembly task, instead of sit down to program the robot how to do this, we will just have a person to do the task, and then we will record their performance through the head-mounted camera, and then translate that to the robotic system. And the reason we want to do this first-person view is because we believe that this is the most natural way of to handle the objects from the person's point of view. And so I'm just going to show you some video later so that you can see why this is better than different viewpoints. But to give you some ideas, just want to show you the kind of task, what it looks like. Right? So participants coming to the lab to do this assembly task. We are recording their first-person view. So this is the third-person view. But from their first point of view, this is the kind of data that we collect. Right? So pick up the tool, pick up different pieces. And again, we are simplifying a lot of perception problem here. We use all different kind of AR tags to sense the objects and configurations. So here's an example when this viewpoint is ideal for the user because the previous demonstration. So it's much easier for the person to do the task with the robot. So the robot will pick up a next piece and present to the user for the user to assemble. So we compare this to a baseline, which is essentially use IKEA's front page as a configuration. And you'll realize, you'll see from the video, like it's very awkward for the person to work with this particular viewpoint. So we, in this project, we explore this first-person demonstration that can capture a more natural way of assembly for the participants. All right, the last principle I want to talk to you about today is error awareness. So we can do end-user programming. We can do all the AI-driven approach for robotic assistants. But at the end of the day, they are going to make mistakes, right? So they won't be perfect all the time. So how can the robot system to be aware of its mistake? So we look at this from the idea of people respond socially to something that's unexpected, right? So we essentially did a data collection study to explore how people respond robot errors. Right, so they will program the robot, but then instead of playing their program, we will play a erroneous program where the robot will make a mistake, and we want to see how they respond. Right, so what we learn is people respond socially to any kind of robot errors. Right, they might show surprise facial expression, they might smile, laugh. They might just like look very suspicious of what's going on in the robotic system. And we actually see this kind of behavior escalate over time, right? So they might start with something mild, for example, raising eyebrow, and then scrunch, and then start to look away, unbelief what's happening, and then smile, and then maybe provide verbal comments. So we see various social responses, this kind of escalation. And the idea that behind what we're doing here is if the robot can sense this kind of social responses, then it's a good indication that it might actually make a mistake. So we are now in a process of doing a larger data collection of this, where doing similar things, the person will provide demonstration, everything looks good. But when the robot play back, the robot will intentionally make a mistake. And we just capture a lot of multimodal information from the user. So this is what it looks like for our data collection. So as the unexpected things happened, the person was surprised and shocked. So we collect a lot of data. Right now, we are doing modeling parts to ideally create something that we can anticipate that an error might happen based on the initial social responses, so that the robot can either stop before the error happens or initiate mitigation strategies early on. But this is still very early work, but we see a lot of potential of leveraging people's natural social responses as a way to increase the robot's awareness of its performance and its capability. So I went through many different projects very quickly today that highlights different principles that we learned from the past few years about building effective human-robot interaction or human-robot teams. And I think there are a lot more to do in this space. For example, how do we quantify, how do we model quote-unquote social norms into robotic systems? What are the longer-term benefit, longer-term impact of this kind of robotic systems on human behavior or just the way people do their work? But yeah, we are seeing a lot of potential for this kind of technology, and see that they are at least in the process of transforming the way people do work at hospital, in public places, even in manufacturing. So I want to stop here, and so that we can have some discussion of questions. But thank you for your time, and I'll be happy to discuss more.